Hello and welcome to Fouraye Academy. Today I'll be teaching financial mathematics. Last episode we looked at the concept of Ito integrals. In this episode I want to expand on the idea of Ito integrals and apply them to general processes. Now, what was our Ito integral? 0 to t of a process or delta t d omega t. Now, we always imagined that delta t was a simple process. However, what would happen if it were not a simple process? If it were not a simple process, but a continuous process, we would have to approximate it through tiny little simple processes. And the more the count of the simple processes get, the more accurate the approximation. So we could simply say delta nt being simple processes as n tends infinity. Alright, now that we know that we can approximate a general process through smaller simple processes, we can now imagine a general Ito integral in a more lucrative sense. Now, let's look at the Ito integral, right? So, limit n tends infinity. Let's look at the partitioned simple processes. So it's going to give us the general process. This is the idea lying between taking the Ito integral of a general process. Now, how do we go about doing this? Let's first look at the expectation. Now, remember from our previous episode, so we'll look at the quadratic variation, right? dt is going to be 0 as n tends to infinity. We'll see that the simple process the difference between the simple process and the general process as n tends to infinity will be 0. So as n tends to infinity, in fact, yes, the simple process will almost surely approximate the general process. So yes, now that we know how we can think of the Ito's integral in terms of general processes instead of simple processes, how do the properties of the Ito integral for general processes differ from that of the simple processes? Because these two are not exactly the same. So first of all, let's define our Ito integral for general processes. Say we have this, our general process over here. This is going to be equal to a Ito integral of simple processes in which the n tends to infinity for that simple process. In fact, we gotta say u. Alright, so yeah. Now let's take a look at the properties. The first property is that the Ito integral it is continuous on a function of t for any given scenarios of omega. The second is that it is sigma algebra F measurable. The third is that it has linearity. So if we have a process A and a process B, we can separate them into two different Ito integrals. Alright. The fourth, which comes from the past one, is that the Ito integral is a martingale. And then the fifth, which we've already seen again in the simple, will carry downwards Ito's isometry. So what was Ito isometry? Ito isometry states that the expected value of the Ito integral squared will simply be a Lebesgue integral of 0 to t of the process. This, in this case, is the general process instead of a simple process. And the quadratic variation is our final property. The quadratic variation is going to simply be the given Lebesgue integral. And quadratic variation is a stochastic process. Meanwhile, Ito's isometry is not a stochastic process because it is an expectation. So now we can imagine how Ito integrals are for, general processes. So how do we go about computing an Ito integral? An Ito integral is quite rigorous to compute, unlike a standard integral. So taking a simple Ito integral, omega t d omega t, right? If this was the Lebesgue integral, it would simply be omega squared t over 2. However, remember that we have quadratic variation. Unlike normal functions, Brownian motion has quadratic variation. Therefore, we must add something relating to quadratic variation to the end. And this proves to be quite troublesome, as it makes the mathematics a lot harder. Now, omega t is a simple process, so we'll create is a general process, so we'll create a simple process at which we will make it to be piecewise, which will return omega of 0 if we have a t value between t and t over n. Now we're partitioning times again. If you remember in our Brownian motion or Ito integral video, we talked about how we partition t over n. And it will return t over n if t lies between tn and 2tn. And it'll return n minus 1 tn if it lies between n minus 1 tn and t. So what we did here is just partition this. So basically what we have is t big T over here. Then we have tn, 2tn, 3tn, and then n minus 1 tn, and then t, right? And of course in the beginning we have 0 or t0. So yeah, now that we've done this, we can now express our general Ito integral in terms of that said simple piecewise function. So it can be expressed as a Ito integral from 0 to t of omega nt d omega t. Now remember how we talked about, how we talked about quadratic variation. First, remember what this is. And then we'll look at quadratic variation and we'll look at how it relates to this, right? So this is simply this. Minus omega j t n. Alright, so this is the Ito integral, right? Now, these are quite long, so we'll simply imagine Wj as Wjtn and Wgj plus 1 as this. So yeah, to simplify our process. Now, take a look at this Ito integral and remember how it looks. Alright. Now, we'll be looking at quadratic variation, since that is the thing that changes this from a normal integral into an Ito integral. Now, what was our Ito integral? We just wrote there. This, right? To n minus 1 of omega j. I will use the shortened notation. Omega j plus 1 minus omega j. Alright, so we have this. Now, remember from the Lebesgue integral, what we got was omega squared t over 2, right? So let's look at half of the quadratic variation. Half of the quadratic variation. What was the quadratic variation? Well, we'll see. It was a summation wj plus 1 minus wj squared. Now, what do we do with this? You may ask. What we do is we separate this into the components. So what we get is simply this. Right? And then minus so what I did there, just open up the square. Alright, so we have this. This j plus 1. So what we do now is we take this j plus 1 to be k and start k from 1. Alright? So what happens when we start k from 1? We'll have a new summation equation. 1 over 2 k equals 1. Ooh, let me write it in a better looking way. 1 over 2 summation k equals 1 n minus 1, or it's n now, of wk squared minus summation of I equals 0 n minus 1 j equals 0 of wj plus 1 plus 1 over 2 summation of j equals 0 n minus 1 wj squared. Alright, we have this expression. Now, what we want to do is we want to start k from 0. So we take out from this 1 over wn squared. So now what we have is 1 over 2 summation k equals 0 n minus 1 wk squared minus summation j equals 0 n minus 1 wj plus 1 plus 1 over 2 summation j equals 0 n minus 1 w squared j. Alright, now we have this. Alright? Yeah, so from here, what we want to do now is to combine these two segments, which we got, these two, into one. Okay? So what we'll have is then 1 over 2 wn plus 1 plus the summation of j equals 0 to n minus 1 of w squared j minus the summation of j equals 0 n minus 1 wj plus 1. Okay, now we have this. Now we want to combine these two. Okay, and what we're going to do is we're going to factor this out. We're going to factor wj out and then have wj minus wj plus 1. As you can see, this is squared, this is this. We take these two out, keep this one minus this one, and we factor this out as this. So what we attain then is 1 over 2 wn squared plus summation of j equals 0 n minus 1 of wj minus wj plus 1. Now this looks quite similar to our Ito integral, right? However, our Ito integral, if you remember, was wj plus 1 minus wj. So what was this equal to in the first place? This was equal to 1 over 2 summation n minus 1 j equals 0 of wj plus 1 minus wj squared. So what we simply do now is to multiply this by negative so that we have plus negative here. And then, since this is now negative, move this over here and move this over here, and we'll attain our Ito integral. And so what we get then is that the summation of n minus 1 j equals 0 of wj plus wj plus 1 minus wj. So what we did here was multiply this by negative and move it onto the other side. So this is now positive, but the inside is this way, and take this over here. And so this is equal to 1 over 2 wn squared minus 1 over 2 summation of j equals 0 n minus 1 wj plus 1 minus wj squared. So if you realize, now we can take the limit as n tends infinity in order to form the Ito integral again, which we formed in the beginning. And we formed it through, and now we formed it through the equation of the quadratic variation. Now you'll see how this is quite useful now, because now that we have this equal to limit n tends infinity 1 over 2 w squared n minus limit n tends infinity of 1 over 2 of j equals 0 n minus 1 wj minus 1 plus 1 minus wj squared. Now you can simply see that this is just half of what we call the quadratic variation. And as n tends infinity for this right here, we'll see that this simply tends towards t, big T. So what we have is that the Ito integral from 0 to t of omega t d omega t will give us 1 over 2 omega squared t minus 1 over 2 quadratic variation of the Brownian motion. Now what was the quadratic variation of the Brownian motion? It would be t. So what we in fact have is this. And this is the Ito integral of the omega t by omega t. And as you can see, unlike a Lebesgue integral, this would be what we have in a Lebesgue integral. We have an added on variable known as the quadratic variation. And that's it for today's episode. Thank you very much, and I hope you like and subscribe.